Okay, welcome everybody to today's webinar. As I said, my name is Jill Browning and I will be your moderator for today's webinar on enhanced softening for drinking water. Before we get into our presentation today, I do have just a few housekeeping slides to go over. First of all, hopefully you should be able to hear me speak now, but I do want to mention, just in case if you do have any difficulties throughout the presentation today, there are two different options or two different ways to connect to the audio. You can use either the computer audio or via your phone. So if one has an issue, feel free to switch over to the other. And then also, due to the large number of attendees that we do have on today's presentation, we have gone ahead and muted everybody's line, but no worries, there are still ways to interact with our speaker today. In terms of interacting with today's presenter, you can ask your questions via the questions panel anytime throughout the webinar. And at the end of the presentation, we have set aside some time for questions for our speaker to answer them. So feel free to ask any questions that may come to mind, and we will try to get through as many of those questions as time allows. Today is the last day in our 3-week live webinar series that we have been conducting. On the screen, you can see the other presentations that we have done these last 3 weeks. And if you have missed any of the previous ones, don't worry. You can still access those recordings on our website over at www.veoliawatertech.com. And in addition to the 3-week series that we did, we have also gone ahead and made available our collection of on-demand webinars that we've conducted over the last few years. So you can also access those on-demand webinars over at www.veoliawatertech.com. One other housekeeping note here is a PDF participation certificate. It will be made available to you at the conclusion of the webinar. You should receive it probably within 24 hours or so of that. So just be on the lookout for that if that is something of interest for you. At the end of today's webinar, you will receive a quick survey requesting your feedback. It should only take 20 to 30 seconds or so. And for those of you who do complete the survey, you'll be entered into a drawing for a chance to win a $25 gift card. So we do ask for, if you would please do that. Okay, now just one more quick slide before I go ahead and introduce our speaker for today's presentation. Veolia Water Technologies, we are a leading company within water treatment. We focus our efforts in 3 key main areas. Technologies, we offer advanced and robust water treatment technologies. We have a large portfolio of over 350 proprietary technologies that we're able to offer our clients. In addition to our technologies, we are able to pair those technologies in terms of developing projects for our customers and also put together multiple technologies to meet required treatment specifications of the client. And then lastly, we have a very thorough service offering that we can provide, whether it's during projects or after. Okay, so now I'd like to introduce our speaker for today. Tom Perry is our panelist for today's presentation on enhanced softening for drinking water. He has been involved in the water and wastewater industry for more than 23 years and is currently the Director of New Product and Market Development for Veolia Water Technologies. Tom, are you with us today?
I'm here, Jill. Thank you very much. Good afternoon, everybody. As Jill mentioned, I will be talking about enhanced softening for water production. In particular, it will be pellet softening. So in the discussion today, I will talk about the where, why, and when to consider pellet softening, go into some specific details of Veolia's Actina pellet softening process, go through some quick process considerations for pellet softening, do a quick comparison between the commonly known softening technologies and pellet softening, and then give you a few examples of installations and talk about our pilot for a little bit. As Jill mentioned at the end, I'll do my best to answer as many questions as you guys throw at us. If we don't get to all of them, we will follow up with those at a later date. Okay, so where, why, and when? So where would you use pellet softening? So this is a pretty typical map. You can find various versions of this on the internet. I like this one in particular because it's a little easier to read, but basically it's just showing you the various groundwater hardness concentrations throughout the United States. In this particular version, the darker the blue, the harder the water. So where would you use pellet softening? So really it just boils down to if the water you are treating has a high level of calcium hardness in it, and or if you remove a majority of that calcium hardness, it'll allow you to meet your total hardness effluent goals, then pellet softening is something worth considering. So why use pellet softening? First off, it's very simple. In our reactor, there's no moving parts. There's a very small process footprint. There is no mechanical dewatering required of our waste. There's no concentrated brine to dispose of. And the pellets that we produce self-dewater and pretty easily get to 95% solids. And on top of that, you can reuse the pellets for other uses. So when to use pellet softening? So if you currently or think in the future you may have some disposal limitations for your lime sludge or brine, if you need to expand capacity at your existing facility, softening facility, but you don't have the space required to do it with the same technology you already have. If you're tired of dealing with the heavily mechanical softening and dewatering equipment associated with a conventional lime softening plant, you can also use it if you have an existing ion exchange softening system and you can pre-treat it with pellet softening. Basically, you're going to lighten the load on your existing ion exchange so you can minimize your brine production, extend your media life, and improve your water quality consistency. And in general, you can use it for any water production needs you have. It's not strictly just for municipal, but you can also use it for industrial water generation as well. Okay, some specific components to Actina pellet softening. So kind of start at the basics. So what is it and what does it do? So pellet softening is a simple fluidized bed reactor that uses a catalyst, and this catalyst can be sand or calcium carbonate pellets that promote calcium carbonate precipitation. This is what a typical reactor, Actina pellet reactor, would look like. So the flow comes in at the bottom, goes up through our fluidized bed, and then comes out through the top of the reactor from a common discharge point. So within that fluidized bed section is where the catalyst stays and remains. So that catalyst, as mentioned before, can be either sand or it can actually be the waste pellets that you produce with the reactor. You can take them and crush them and reuse them in the reactor as catalyst. So what does it do? So it reduces calcium hardness while producing a usable, easily dewatered pellet. So this is what the pellets look like after they've been dewatered. So how does the influent flow get distributed through the reactor? So again, you can see our typical reactor. And at the bottom of our reactor is a strainer plate, which has numerous flow distribution strainers. So if you take this portion and bring it over to the side, so what you're looking at is the top of that section is the strainer plate, and each one of those items you see on the top is individual strainers. So if you just take one of those strainers and blow it up, that's what it looks like. So these strainers are fastened to the strainer plate. So they go through a hole in the strainer plate. That top piece that you see there is on the discharge side of the strainer plate, if you will. And then at the bottom, the strainer is attached to the plate with a nut. We have specifically designed strainers that are used, again, specifically for pellet softening. And this allows us to have equal distribution of the flow up through the reactor, but it also allows us to pass any material that may come in with your groundwater supply or hard water supply, like small sand particles or what have you. And we do that by the way it's set up. So the strainer is in two pieces. And if you look at about midway on that picture to the left, there's a lip. So that lip actually sits on the strainer plate. On the bottom of that, the nut comes up through and fastens it to the plate. So the flow comes up through the middle of the stem, exits out these holes here. And this cap you see actually sits on top of that stem. So the complete picture, if you will, is the first one I showed you to the right. So again, those holes in the stem and then those openings on the cap are what evenly distribute the flow, and it allows for any material that may come in with the flow to pass through the strainer. So this is what it looks like looking down on top of the strainer plate, and say in real life, if you will. So it looks like birthday candles, but those are all individual strainers installed in the strainer plate. So pellet softening is very simple, but there's a few critical components to it, and equal flow distribution is one of those critical components. And as mentioned before, we have designed specific strainers for pellet softening that allow us to accomplish that goal. Okay, so what chemicals are required? So to get the calcium carbonate to precipitate, you have to increase the pH, generally in a 9 to 9.5 range. You can do that with caustic soda or lime. As mentioned before, the fluidized bed has catalysts in it, and that can be sand or it can be calcium carbonate pellets. And then the softened water, so basically the flow that leaves the Actina reactor, you'll want to drop that pH back down to close to neutral so that you stop that precipitation reaction. So if this was a drinking water application, you'd want to stop that precipitation reaction before you went to a filtration step. So let's focus on the pH adjustment first. Again, same typical reactor. So what we do is, again, whether it's caustic or lime, we inject it into nozzles that are at the bottom of the reactor. Those nozzles are in what we call a spider, and the spider is removable. And I'll get into more details here. But what we do is we bring the pH adjustment chemical and softened carrier water together at these nozzles so that it disperses equally across the bottom of the reactor. So if you look at the bottom, again, the previous pictures I showed you, the blue is the strainer plate and the goldish color are the strainers. And what you see immediately above that in that circular support structure is our spider. And you can see there's 3 nozzles mounted on that spider. So this is what it looks like in real life. So you have the circular support structure, and you can see in the middle, it's attached to a line that comes from the top of the reactor, which allows you to remove it. But also you see on each nozzle, there's 2 chem feed lines going into each nozzle. So each one of those is the pH adjustment chemical, and one is the carrier water. So they come together in the nozzle under pressure, come out through the bottom, and that evenly disperses the chemical throughout the reactor. For this particular size reactor, there was 3 nozzles on the spider. Again, these nozzles that we use are something that we have developed over years of experience to evenly distribute that pH adjustment chemical across the reactor cross section. Just a quick close-up of what that looks like. It's pretty simple, but effective. And what we do on each of those nozzles, again, you have the chemical adjustment line going into the nozzle, then you have the carrier water line going in. So we actually have flow meters, generally a rotometer, on each one of those lines going into each of the nozzles. So as you can imagine, this spider is sitting at the bottom of the reactor, and we have these rotometers that are up above so that you can monitor how much of the pH adjustment chemical and how much of the carrier water is going to each nozzle. So if there was ever a time where you saw that one was getting more flow than the other, again, that's the intent of being able to pull this thing out of the reactor real easy, check it out, and then put it back into place. And I'll show you more on that here in a minute. Okay, so the other chemicals I'd mentioned, the fluidized bed, I'm sorry, the catalyst, and then the pH adjustment after it's been softened. So the catalyst, again, it can be either sand or it can be calcium carbonate pellets, but you can add it either by pump or by inductor, and it goes into either the side of the reactor or you can actually just drop it right into the top. So here's a couple examples. So the one on the left is just a slurry tank, and you can see there's a small conveyor that comes through the wall on the right-hand side. So that's just dropping the catalyst, whether it's sand or pellets, into this slurry tank, and then you can pump from that slurry tank into the reactor. Even a more simple approach is the one in the middle where you see the blue funnel, and that's basically just an inductor. So again, kind of in the middle of the picture, you see a similar conveyor that's going to convey that sand or calcium carbonate pellets, drop it into the funnel, then you just have plant water under pressure, forms an induction, and then that plant water carries the catalyst into the reactor, again, either into the side or you can drop it straight into the top. So you add fresh catalysts periodically over the course of the day. It really depends on how frequently you are extracting, but I would say typically it may be 3 to 4 times a day. Going back to the post pH adjustment, so this is added into the effluent of the reactor, and it can be as simple as dropping some type of acid into the outer ring of the effluent weir on the top, just so that you bring that pH back down to close to 7, again, to stop that precipitation reaction before it goes downstream. You can also use CO2. It can be in line just downstream of the common effluent from each reactor. Okay, when and how are the mature pellets extracted? So we continually monitor the pressure above and below the strainer plate. So in this picture, you can see the pressure sensors above and below the strainer plate. I don't know how well it shows up, but the strainer plate is welded to the inside of the reactor, and you can see those weld marks. So we have the pressure indication above and below. So during commissioning, we will kind of do some trial and error, and we will determine the differential pressure associated to certain pellet size. So the longer you run without extraction, the bigger the pellets grow inside the reactor. So what you're trying to achieve is you want the pellets to be as big as possible, but not too big, because A, it's a fluidized bed, so you want the pellets to still be fluidized, but you don't want them to get too large. So just being a fluidized bed reactor, the larger pellets will be closer to the bottom of the reactor. So that's where we extract the pellets when the time comes. So the pellet extraction is just a pipe that comes off the side of the reactor. And again, you can see just below that is where the strainer plate is. You can see the weld marks. So once that differential pressure is reached, or it can actually be done on a timer. It can just be a certain frequency of time that the reactor's been running, but when it extracts, it can be extracted either by pump or by gravity, and it's a timer. It just opens that valve for a certain amount of time and then closes it. And once the extraction is completed, we have the ability to flush the line with some plant water just to get out any remaining pellets that may be between the extraction point and where you actually end up discharging the pellets. So both the pellet extraction and the catalyst addition is all automatic. So this is all done through a PLC controls, very simple, and we don't stop the influent flow during catalyst addition or extraction. So you're always treating water even when you're doing these two exercises. Okay, so once you extract the pellets, how are they dewatered and handled? So as I'd mentioned before, our pellets are self-draining, so there's no mechanical dewatering required. So most of the time, you can just use a simple bin that has a retaining screen at the bottom so that it retains the pellets, but it allows water to drain through. And most of the time, it's either a single bin or it can be a double bin. So if you look at the top one, you can see there's a Schedule 80 PVC pipe coming out of the building that goes straight into this bin. This one in particular just has a cover that they can pull over the bin since it's outside to keep the rainwater off it. If you look at the two bin scenario down below, it's kind of a duty standby thing where you have just a cover to keep the rain off it. But if you get a little closer look at this two bin scenario, so these bins are sloped from the back towards the front. And in this one, you can see the water actually draining off the drain spouts at the front of the bin. The PVC pipe you see kind of in the middle, that has a rope attached to it, and you can move where the pellets are discharged into the bin, and you can swing the discharge point between the two bins. So very simple. For larger facilities, you may require an actual silo for the pellets, and then a more sophisticated scenario where you have more truck offloading. But for a vast majority of the projects that I've seen, just the standard bins is more than enough. Okay, here's an operational video I want to show you. And this is looking down from the top of the reactor into, I would say down on top of the fluidized bed. And I'll show this to you twice. It's short, but I want to talk you through a few things. So when you look now, before I started, there's a cable that runs down on the right-hand side. So that is the cable that is attached to the spider that's at the bottom of the reactor. This particular plant, they had put some red tape on that line so that they know when the spider is all the way down at the bottom. But there's also feet at the bottom of the reactor, so you know when the spider is set in place. But for this one, they just happen to have tape onto the line as a double check. So let me get this video going. So again, you're looking down on top of the fluidized bed portion. So what you can see is that our nozzles are doing a really good job of evenly distributing the flow, getting a good churning of the pellets. So the fluidized bed contains pellets and sand of various sizes and various stages of development. All around the top of the reactor is just a weir that collects the softened water, and then it discharges from a common location. Let me get my cursor here. Let me show it to you one more time. So those lines you see going into the fluidized bed, those are the chemical feed lines that are going down to the spider. So there's two going to each nozzle. And in this particular installation, they have 3 nozzles on the spider, like the example I had showed you earlier. And that instrument you see in the top right-hand corner is a online turbidimeter. Okay, next video I want to show you is the actual extraction of the spider. So again, very simple hoist. Bring it up when you want to inspect it for whatever reason. This whole process took about 5 minutes. You know, it's just kind of showing you the end of it as the spider got close to the top. In the background, you can see the panel. So you can see the chemical feed lines that are coming out of that panel. So that panel is where the rotometers are contained so that you can double check that all the nozzles at the bottom are getting equal flow of both carrier water and the pH chemical. So you bring it up to the top, you can do what you need to do, you can inspect it. Normally they'll be able to lift the spider above the top of the reactor and then swing it over to the side. And then if you have grating or a checker plate or something next to the reactor, you can just drop this down and do what you need to do without, you know, reaching over the water in the reactor. And then when you're done, hoist it back up with the hoist and drop it back in. So when you extract it, you shut the water flow off to the reactor, but when you want to put it back in, you do need to have the bed fluidized so that it goes back through the media pretty easily. But very simple, again, very easy. Takes about 5 minutes to pull it out. So this third video I wanted to show you, this is actually pellets being extracted. So this goes back to that double bin setup that I had showed you previously. So again, you can see the PVC pipe where the pellets are being extracted from. Now you can actually see the rope that's attached to it, so they can move that PVC pipe to, you know, change where the discharge hits the bin. But what I want you to watch is to the left of the video. As more pellets and water begin to be introduced into the bin, you can see how the water starts to run off the pellets. So what you're going to see is just the water that's, you know, running off the top. And I'll show you here and at the end of the video, you'll see where the water is actually draining through the pellets and coming out through the base of the bin as well. But you see, as more pellets get introduced into the bin, the water is just running right off the pellets. So when I mentioned earlier, there is no mechanical dewatering required. That is because these pellets, if you think of it, they're like 1 millimeter marbles, almost 2 millimeter. So the water, again, there's easily self-dewatering. And at the end of the video there, you can see how the water is just draining right off the bin. In this particular installation, let me show you that video one more time. So in the beginning, you can kind of see this particular installation is surrounded by farmland, and they actually have no waste. The farmers come once a month, take their pellets, and they use them for fill around their property. So this particular plant, at least when I was there last year, had told us that they don't have any waste that they have to deal with. It's all taken away by the local farmers. Stop that. Okay, some quick process considerations when you're thinking about using pellet softening. So again, you're going to get calcium hardness reduction. It's going to be anywhere from 80 to 95%, and that range is controlled by what pH you operate at. So if you want to get lower calcium hardness reduction, you can feed less pH chemical. If you want to get more, you run at a higher pH. So you do get some magnesium hardness reduction, around 5%, and that can go up a little bit. You can run this up in the pH 10, 10 and a half, but you don't get a whole lot. So I would say majority of the hardness reduction you're going to see is going to be through calcium hardness reduction. You know, a lot of people want to know, well, how much pellets am I going to produce? And it depends on a lot of different variables. What pH you're running at, which pH chemical you're going to use. You actually will produce twice as much pellets if you use lime versus caustic. obviously how much hardness you're removing, so on and so forth. But as an example, if you had a 2 MGD facility and you were removing 200 milligrams per liter of calcium carbonate, you doing 24 hours a day with caustic, you would produce about 3,000 pounds a day of pellets. The density of a 1 millimeter pellet is about 100 pounds per cubic foot. Your pellets could be anywhere from 1 to 3 millimeters in diameter when you extract them, but generally just use 1 millimeter as a point of reference. So when it comes to sand use, if you're using sand as a catalyst, again, same things kind of dictate how much sand you're going to use, but if you took the same example, you would use about 25 pounds per day of catalyst. Now, I had mentioned before, so you can actually take your extracted pellets, which are going to be anywhere from 1 to 3 millimeter in size, crush them, and then put them back into the reactor and reuse them as catalysts. But if you're using sand, this is an estimated amount of sand based on that operating condition. Okay, some quick comparisons of, I would say, the commonly used softening technologies. So you got pellet softening, ion exchange, conventional lime softening, and then nanofiltration. So real basic stuff. CapEx, low to high from top to bottom. OpEx, similar. Operation, from top to bottom, it starts simple and it gets a little more complex. Obviously the footprint from a lime softening facility, when you include the mechanical dewatering and things, is quite large, where ion exchange and pellet softening are relatively small, and I would say nanofiltration is in the moderate range. So sludge and waste handling. So again, the pellet softening, they self-dewater and you can reuse them. The ion exchange, when I say low OpEx, I would say if you have an easy way to dispose of your regeneration brine, then your OpEx is pretty low. But if you have issues with getting rid of that brine, then that can change that OpEx to being quite high. So it really depends on your particular situation. The same holds true for any nanofiltration. You're going to have that brine you're going to have to dispose of. And of course, for conventional lime softening, as I mentioned, you have the mechanical sludge dewatering that you have to deal with. Any unique components? So like I mentioned earlier, for Actina pellet softening, we have our strainers at the bottom, and then we have our spider, or removable spider, where we inject our pH chemicals. And then we also have Aquavista through Veolia, which is a way to remotely monitor your facility. If you look at ion exchange, you may have some proprietary resins. Nanofiltration, of course, you got the membrane replacement costs. And then one of the good things about chemical, lime softening is it's pretty straightforward and no real unique components to it. So when you look at performance, going back to one of my earlier slides, so the ion exchange, lime softening, and nanofiltration do a really good job at both calcium and magnesium hardness reduction. But if you can achieve your total hardness goals by just removing the calcium hardness, you could have a much simpler technology. If you don't need to get rid of the magnesium hardness, there's a much simpler way to get there, is my point here. So quick summary: low CapEx, low OpEx, simple, small footprint, but it is tall, but it has a small footprint. And as I mentioned before, you can reuse the pellets. You can use them as construction fill, or as I mentioned in that one particular facility, the farmers come and take it. I've seen where you can use it in the production of concrete, animal nutritional supplement, and you could even use it for landscaping. I mean, it's literally small, nicely circular white pellets that you can easily just put in landscaping just as they are. Okay, a couple more slides. Talk about our pilot first. So we have pilots that are rated 10 to 14 gallons a minute. And we basically have two skids associated with each pilot. One will be the reactor and one will be the control panel with some chemical feed equipment. So here's an example of a pilot. The first to the left is the reactor, and then the control panel skid, and then the picture in the middle is just the same two skids, just at a different angle. We can use them with caustic or lime, and we do have automatic control of the pellet extraction. So if you look at the picture to the left, the pellets are extracted right here, kind of the same way they would be on a full scale. It's just by gravity, and you open that valve for a certain amount of time and then close it. The one thing that we have is we can put in different lengths into our reactor to make it taller, depending on the water quality, if it's how hard the water is and what level of hardness reduction you're trying to achieve. So we do have some additional flexibility with our pilots to test various different heights depending on the need for the application. Couple of quick installation slides. So we have 50 plus worldwide, over 30 years of design experience. It's one of those things that's been around for a long time, especially over in Europe, but it's not well known here in the US. So some people are shocked when I tell them that we have 50 installations and Veolia has been doing it for over 30 years. We have a wide range of installations, with our biggest at 80 million gallons a day and smallest at 0.4. Here's some additional breakdown of our installation base, but really most of the jobs that I've been pursuing or been working on in the US have kind of fallen in this general range. So we have a really good installation base in that smaller flow range. Of course, with 30 years of experience, we bring a lot of to the table, but a lot of these plants we have in Europe are also operated by Veolia. So not only do we get engineering design feedback, but we also get some really good operational feedback as well. So anything we do now benefits from that 30 years of experience around the world. A couple examples, Copenhagen and Denmark. This particular water authority has 7 regional treatment plants. They range from 3 to 13 MGD, and eventually all 7 will have Actina pellet softening. So if someone wanted to go visit some installations, you can go, and these different installations are all in different say stages. Some are in operation, some are under construction, some are under design. So it's a pretty neat opportunity to go see these different ones. So an example of one of them in Denmark, this one just happens to have 3 reactors. You can see in the middle picture there, 0.6 million gallons each, followed by media filtration. This one was commissioned in 2017. Here's another one in Denmark. Again, it falls under these 7 different plants that this one municipality is doing. This one, I believe, is under construction. 4 pellet reactors, media filters. Very similar. This one is kind of being done completely by Veolia, so there's a lot of good design and control experience that we can bring to the table. If France is more your thing, here's an example. This one actually has 1 single pellet reactor, about 1.2 million gallons a day. The picture to the left, you can see they also have a CO2 stripping tower. Obviously, this is groundwater, followed by media filtration. This one was commissioned in 2015. Most people ask, are the tanks generally made of stainless steel? And I would say yes, the reactors are more often than not made of stainless steel. Something a little closer to home, we have currently under construction in South Adams County, Colorado. We'll be providing 3 pellet reactors, each rated at 4.6 million gallons a day. They'll be followed by media filtration, and again, they'll have the ion exchange for the carrier water for the pH adjustment, which will be caustic. It's under construction, operational summer 2020 was the last I heard. Here is kind of a courtesy of Carollo Engineering, a general layout of the pellet reactors and the media filters. Here's a pictorial of the reactors that we'll be providing. So each reactor is roughly 25 feet tall, and that top diameter is roughly 17 feet. If you get in a little closer to the reactor portion of the project, I had mentioned we're only providing 3 reactors currently. They have a space allotted for a 4th reactor for future expansion. In that picture in the middle, you can see kind of in the top left side. So they're actually going to have storage bins that are elevated. So those bins are going to basically hold the pellets, dewater the pellets, and then they're situated so that a truck can pull in underneath and they can empty those bins into the truck and then continue going on. So as I mentioned before, depending on how many pellets you produce, you may need something more than just those bins. And this one in particular in South Adams County has individual bins that are elevated above a truck entryway. Here's a recent picture from just last week, I believe, or this was probably a couple weeks ago. So there's 2 of our reactors currently installed. And then this one was late last week, I think. So you can see all 3 reactors have been put in place, and they're starting to build the building around it. Quick wrap up. So Actina pellet softening, it's simple to operate. We have self-dewatering pellets, 30+ years of experience and expertise, and we do have demonstration units available that we can bring, treat your water on site, and come up with some really solid operating costs, CapEx costs, and let you see how it operates, what the pellets look like, and so on and so forth. So with that, I think we got a couple minutes left for questions. Jill?
Yes. Yep. Thank you very much, Tom. Just want to do a quick reminder. Any questions that you may have, feel free to type those over in the questions panel. And with that, I will go ahead, and we did have some questions that came in throughout, so I will go ahead and kick off this Q&A session.
Okay.
Tom, one question is, how do you combat turbidity in the effluent?
So generally for say a drinking water application, you will need a filtration step downstream. It could be a typical dual media filtration. If you're treating groundwater, like say if you're an existing groundwater facility and you don't have to filter your water, but now you want to soften it, you have a lot of flexibility in how you can operate those filters. So you can typically just use them as a solid capture step. So you don't have to be, in that 4 to 5 gallon per minute range. You can be much higher. So you could even possibly use a 10 micron disc filter. So if you're truly just trying to capture some solids, there's a couple different ways you can get it. If for a drinking water application, if you have that filtration waiver already, if you don't have that filtration waiver, then you would do a typical dual media filter.
Great, thank you. Another question that came in is, what is the recommended temperature in the reactor?
So it'll be ambient. Again, if you're doing groundwater, it's usually pretty stable. You will see some impacts on performance as the temperature changes, I believe above 70 degrees Fahrenheit. It's not catastrophic by any means, but you do have to take temperature in consideration. But if you're thinking a lot of times it's maybe in the 50 degree Fahrenheit for groundwater, I mean, that's perfectly fine. So if you have a water source that is higher, say like an industrial application maybe, we can talk about it and look through and see what impacts that temperature may have. But ambient is fine. We don't really have to do any particular temperature for performance.
Okay, a question on the design. What is the typical design overflow rate?
We're generally in the 80 to 100 cubic meters per hour.
Okay, and also what concentrations of iron and manganese can this process manage?
Yeah, great question. Generally, we're in the range of the 80 to 90% reduction for both iron and manganese.
Okay,
And they will
oops.
precipitate with the pellets. So if you're just getting calcium hardness reduction, the pellets will be nice and crystal white. They're nice and clean and white. If you have some iron and manganese, you will have the pellets be discolored, but everything will precipitate out with the pellets.
Okay, we've got time for a couple more questions here. Has this ever been used for, say, sulfate removal?
Good question. I would say I don't know the answer to that one, but Jill, if you can know who asked it, I can get back to them.
Yep, absolutely, will do. Another question that came in here is, what is the typical concentration range of calcium treated within the reactor?
Say it again.
Yep, so talking about the typical concentration range of calcium within the reactor.
So let me see if I can answer that or make sure I got the question right. So if you're doing a groundwater application, you know, the influent total hardness could be anywhere from, 200 milligrams per liter up to 2,000 or 1,000. Basically, you're going to be removing 80 to 95% of the calcium hardness, and everything that you're removing is basically bound up in those pellets. So I don't know if I answered the question or not, but generally on the effluent side, we can be as low as 50 milligrams per liter of calcium hardness, up to 200. It really depends on how you operate the process, what pH you operate, and what fraction of the total hardness is calcium hardness on your water. So hopefully that answered that question.
Great, thank you. One final question here. Unfortunately, we're running short on time, but do want to remind everybody, if we weren't able to get to your questions, we will follow back up with you individually there. So to wrap up, Tom, let me see, where was this? Talking in terms of the sizing of the different units, what is the largest unit by throughput?
So when you look at the South Adams County project, which each reactor is sized for 4.6 million gallons a day. We delivered that in multiple pieces. I can't remember if it was 2 or 3, but when you look at the top diameter of 17 feet, it gets to be a bit of a challenge from a transport scenario. So we can make them pretty much as big as we want, but you have to kind of look at what logistically makes sense. So I would say in that 5 million gallons a day range is reasonable. Much bigger than that, we kind of have to take a hard look at the design and try to make sure that it doesn't, it's not an outrageous cost to deliver it from our fabrication site to the plant. So 5 MGD, I guess, is a good benchmark.
Great. Well, thank you very much for that very informative presentation for us today, Tom. And we do thank everybody else for joining us as well. As mentioned, we will get back to you if we did not get to your questions. One other thing to note, we are recording this presentation today, so that will be sent out to you probably within 24 hours or so. You will receive a copy of that. And we do thank you for your time, and we do appreciate if you would fill out the survey at the conclusion of today's webinar. And for those that do complete that survey, you will be entered to win that $25 Amazon gift card. So with that, that concludes today's webinar, and we do thank you for your time.
Thanks, everybody.